That. Thank you, Gordon. Okay, start again. It's a pleasure to have Joan Licata from Australia National University, who will tell us about bordered Heegaard Floer invariants for contact manifolds. I think if you have questions you want to ask in the middle, just unmute yourself and speak, because I'm not a very good moderator in terms of watching the chat, unless Joan is good at watching chat. But probably just it's small enough group, so just speak when you want to speak. Right, Joan?
Sounds great.
Okay, great. Go for it.
Okay, well, thanks so much for the invitation. I've always enjoyed my visits to Athens, and since that's not in the cards, it's great to be there virtually. So I should say, I think more significant than where I am physically, this is a talk. I'm coming from the future, so it's very early Tuesday morning for me. So my defense, if anything goes badly, is that I have not yet had coffee. And then a coffee cup appears on somebody's picture. So I can see the chat, so feel free to try the chat, but just go ahead and unmute. Yeah, my title is there. This is bordered Heegaard Floer homology and bordered Heegaard Floer invariants for contact manifolds. Sorry, I'm just opening up one PDF as I do this. And I'll start with maybe the most important thing, which is my collaborators. So this is joint work with Akram and also Victoria Feldvari, Kristen Hendricks, Ina Petkova, and Vera Vertucci. And let me start with the sort of very big picture overview. So this is the objects that I want to talk about. So I want to talk on the one hand about contact manifolds, I want to talk about open books, and I want to talk about Heegaard Floer invariants. And I think people have probably seen these in one form or another. So somehow they're all things with very different flavors. Contact manifolds is something geometric, a geometric structure you can add. An open book is a topological decomposition of a three-manifold. And a Heegaard Floer theory is a giant algebraic machine which produces invariants of three manifolds, but also lots of other things. So it's certainly not a new idea to try to relate these. There's been a lot of really fantastic work in this area. And I want to spend just a little bit more time on this slide. Don't panic. It's mostly just an overview trying to say something about the kind of relationships and objects that are already known. So the organization is intended to be the same as the previous slide. So on the left, we have contact manifolds. In the middle are open books. And on the right are Heegaard Floer theories of various flavors. And one of the points here is that there's a lot of these things already floating around. So let me just look through this web for a moment. So the simplest thing we could consider is a contact manifold, a closed contact three manifold. And I should say that all of my contact manifolds are three manifolds. And then maybe the next most general thing you could do is you could allow three manifolds with boundary. And in that case, we want to impose this condition that the boundary is convex. So at a practical level, what convex means is that you have like a little buffer here where nothing interesting happens, where the contact structure just translates but doesn't change in any other interesting way. So a contact structure is a nowhere integrable plane field. So that tells us that the planes are going to be twisting as they move through the manifold on some axis. And when you say that your boundary is convex, one of the things you're saying is that you don't have any twisting in this vertical direction. You're only twisting horizontally. So this is always the condition I'm going to impose if I'm talking about a manifold with boundary. So even if I don't say convex, I'm thinking convex. Feel free to ask if it's unclear. So
vertically means in your picture vertical, right?
Yes, sorry, vertically
vertical
means
is
in
transverse,
my picture.
Yeah.
Yeah. So I'm saying that you have your convex boundary and you can translate it parallel to the surface in some parameterization and nothing changes. So moving to the middle column, we have an open book decomposition. And these go back quite a ways to work of Thurston and Winkelkemper, but they were really brought to prominence in contact geometry by Giroux, who showed that his famous correspondence has said that if you want to study contact manifolds up to a natural equivalence, then you can study these open book decompositions up to some move relating them. And this has been a really profitable approach. A lot of great work in contact geometry has come out of this. And it was extended by Honda, Kazez, and Matic to the case of contact manifolds with convex boundary as a partial open book. And we'll come back to these with a bit more detail, but I just want to highlight one thing that comes out of the notation. So even without having said what these things are, what I'm saying in this top part here is that the data of an open book is two things, and the data of a partial open book is three things. And this is a theme that's going to come up, is that when we want to keep track of what's happening on the boundary, we're going to need more data, more information. And turns out if we want to keep track of more information on the boundary, which we'll do shortly, then we're going to need to have sort of even more different kinds of pieces. But I'll make that a little more precise. And then over here in the final column is Heegaard Floer homology. So this was introduced around the turn of the millennium by Ojvat and Sabo, and many people have worked on it. And it comes in quite a number of flavors, as I said. The simplest thing you can consider is the HF hat theory. So this associates to a closed three-manifold some graded abelian groups. And for basically any kind of manifold you could think of, there's a variation of Heegaard Floer homology that gives that gives you an invariant. So you can imagine doing two things if you wanted to make things more complicated. You could say, let's take this basic HF hat invariant and try to look at more sophisticated algebraic tools. So this leads us to things like HF plus, HF minus, HF infinity, and so on. Or you could say, well, let's try to generalize the kind of object this is an invariant of, like allowing manifolds with boundary. And what I've put here is meant to be that second kind of generalization. So if you consider a sutured manifold, which I'm not going to define, but it's a kind of manifold with boundary, then you get the sutured Floer homology that was introduced by Juhas. And then you can do more. There's other kinds of boundary conditions you can apply besides these sutured ones. And the work that's going to be most relevant is the bordered Floer homology of Lipschitz, Ojvat, and Sabo, and the bordered sutured Floer homology of Riemann-Zarev. And in both cases, these are theories of contact manifolds with boundary, but the boundaries are what's called parametrized. So they're identified with a neighborhood of some graph, and the whole theory is really built to be optimized for gluing. So without really saying what it is, I want to say what it's for. So there's got a lot of nice factorial properties, but really it's designed to be a theory where things can glue really easily. And the reason that there's these three things on the same sheet is that the relationship between contact manifolds and open books has allowed people to define invariants in Heegaard Floer homology. So the first one of these was done by Ojvat and Sabo. It's on this arrow right here. And the same invariant was then recast by Honda, Kazez, and Matic to give an invariant of a contact manifold via open books, but of the contact manifold itself in the Heegaard Floer homology of the manifold with the negative orientation. And it's not just that one can do this, but it's a good invariant. So right down at the bottom, I have a couple of properties here. So that if your contact manifold is over-twisted, which is one of the things you might want to know about a contact manifold, is it over-twisted? Is it over-tight? Is it fillable? Things like this. Then the Heegaard Floer invariant does a good job detecting this in certain cases. If it's over-twisted, the contact invariant in Heegaard Floer homology will vanish. If the manifold is Stein-fillable, some version of being a boundary of a symplectic manifold, then the contact invariant won't vanish. So this is the kind of invariant we want because it's really probing exactly the kind of behavior that we're interested in way over here on this first column. So the other thing that we see is that if you follow across the second row with a little bit of a slant, that from a contact manifold convex boundary, we have this partial open book construction, and then that leads to, again by HKM, invariant that lives in the sutured Floer homology of the manifold with the negative orientation. So what you're supposed to notice here, though, is that there's some space. So one of the main things I want to do in the talk today is try to fill in this space. So this is sort of the lay of the land as of 2019. And I think we can all agree the biggest difference between 2019 and 2020 is the addition of new techniques for studying contact manifolds. Not much else has changed. But the work I want to talk about today is what appears in green here. So we have these nice collection of Heegaard Floer theories. Every Heegaard Floer theory deserves its own contact manifold. That's sort of our slogan. So what I want to talk about is, first and foremost, if we introduce a new flavor of contact manifold over here on the left, so call this a contact manifold with foliated boundary, then we can associate to it a new kind of open book, a foliated open book, and this arrow is going to be the kind of sort of robust arrow that's parallel to the ones above. So if we have a contact manifold with foliated boundary, whatever that is, and why ever we might want to study one, then we'll be able to describe it with a foliated open book. If we have a foliated open book, we get a contact manifold. So we see some parallel structure, but the sort of point of doing this also is that then it allows us to give an invariant for contact manifolds that lives over here in this corner down here in the bordered sutured Floer homology. Okay, so maybe we'll come back to this slide, but let me just say this kind of clearly. Here are the goals. So one, define a contact invariant in bordered Heegaard Floer homology. The second thing I want to do is describe some sort of user-friendly gluing for open books. And this is, the first goal is the kind of goal you can state in general. The second and third goals are really the kind of goals you state after you've done something. You say, what did I do and how could I phrase this as a goal? So I want to kind of tell you that we're going to give a nice way to glue open books together that doesn't take a lot of technical expertise. And finally, I want to describe an easy construction of an open book. So what I mean by this is that we have existence theorems that if you have a closed contact manifold, it has an open book. If you have a contact manifold with convex boundary, it has a partial open book. But actually constructing these in general, if you take your favorite contact manifold boundary, it could be difficult to construct a partial open book for it. And we want to do something. It's like the difference between driving a stick shift and an automatic. So there's sort of art and fun in knowing how to shift smoothly, but sometimes it's nice just to be able to push the gas and go. So this is quite a long time to go without a picture. So let me do something about this. So this is going to be addressing that third goal that I said that's an easy way to construct a contact manifold with boundary that has some flavor of open book decomposition associated to it. Okay, so this is meant to be the classic definition. If you haven't seen open book decompositions before, I'm hoping this will be sort of an intuitive way to follow through. If you have seen them, then just bear with me. So we say that B pi is an open book if three things hold. So first of all, B is some oriented link. Second, pi on the complement of the binding is a fibration over S1. And then we have a framing condition. If you look at each of these fibers, sorry, let me label this. So this was pi inverse of T is what we call ST. So this thing ST is some surface, the fiber of the fibration, and it's bounded by the binding. Okay, so this is the local picture you have over here, which says that near the binding, all of these fibers and come in and meet like the pages of an open book. And so we call these surfaces pages. So we're interested in these as a tool to study contact manifolds. So let's complicate this definition a little bit. Okay, so we now want to consider not just a topological three-manifold, but one that supports a particular context structure. And so just as we've broken our manifold into three pieces, we have a compatibility condition between the context structure and the piece of the manifold for each of these. So if we assume that our context structure is given by the kernel of some one form alpha, then we require that alpha evaluates positively on the tangent to the binding, and this tells us that the contact planes are transversal along the binding. And the second condition is that d alpha restricted to each page is an area form. Okay? And we'll talk a little bit more about what that means shortly. So the sort of takeaway from this is that an open book splits your manifold into two pieces. There's a part that's near the binding, which is standard, and there's a part that's away from the binding, which is just a product of, or a twisted product of some surfaces. So locally, it just looks like a product. Globally, it's some foliation, some mapping torus. Okay. Now, what I said we wanted to do was get a way to get a manifold with boundary, and this is just for closed manifolds. And so we could do the simplest thing possible, which is that into one of these open books, just map in some separating surface. Okay. And one way you could get a manifold with boundary is to just throw away everything on one side of that surface, and that's what we're going to do. So this is the picture where I've taken the surface from the previous page, I've embedded it into the open book so that it bounds a solid torus, and then I've thrown away everything outside the solid torus. And I want to sort of look at the structure we get and then the punchline on the next page is going to be that this, in fact, is an example of a kind of open book that we can use to study contact manifolds. Okay, so let's just look at what we get. We had a binding in pages initially, and now we just look at the restriction to this solid torus, and we still have a binding. This time it consists of these two vertical green intervals. So there's two intervals here. And we have these pages, which are just the subsurfaces of the original pages as they intersected the torus. So the reason I like this example is that it's meant to seem immediate. You put a surface in an open book, you throw away the outside, and you just get this. So you can think about what happens as you rotate around by t. What are you going to get the intersection of that surface with the solid torus? Well, it's going to change as t changes. You're going to have some, if we took sort of the thing sticking right off to the left here, then you're going to have a single component that looks like an old-fashioned telephone. And then as you rotate around to the front, this is going to separate into two components. You keep rotating around, it's going to join up again, it's going to separate. And as you go around, you see multiple changes in the topology of the page. And there's an extra piece of structure that we get, which is that on the surface that we use to cut out this manifold, the level sets of this function pi, so the pages themselves, print a foliation, a singular foliation. And the picture at the bottom unfolds this from the torus. So this is just meant to be the standard identified torus, top and bottom, left and right. And what we have is that the intersection of that surface with each of the pages gives us some curve, possibly with singular points on the torus. And we have names for the kinds of singular points. So we have an elliptic point, like at the center or at the top or at the corners. And these can be, let's leave it at elliptic points. And we have hyperbolic points, like we have one in each of these four squares. And if you look at this example, and this is what the color coding is intended to help a little bit, the hyperbolic points appear exactly when you make the transition between topological types of two consecutive pages. And the elliptic points happen where you have the binding intersecting the surface. So before saying anything formal about this, this is a good time to kind of pause and make sure the setup is clear. If there's any questions, now's a great time to ask before we say some precise things.
I know you told me this before, but I forget. So do you allow for the, I mean, if you had a little bump on that torus, you could also have like concentric circles in your foliation.
That's right. So we could have concentric circles if you just put a torus in, or for example, if you put the torus in sideways so it went around the binding, and we're not going to allow that. So in particular, no circular leaves. Yeah. Any other questions? Okay, then let's put a name to these things. Okay. So we say that B pi F is a foliated open book for a manifold, contact manifold with foliated boundary. So my F is my foliation, if the following properties hold. So the first one is that B is a properly embedded one manifold. In this particular case, my binding is just two intervals, but in general, you could also have circle components of the binding. As before, pi from the manifold minus the binding, it is a map to S1. We asked that this is a regular map. And now I have some fine print. This is one of the fun things about an iPad is the fine print can actually be fine print. So the next couple of points, I don't know how easy they are to read. I put them there to be honest but not distracting, is that, again, we call the preimage of T a page, and the pages are cornered surfaces. So each, if you can see this in the sample pages here, the binding of each page consists of some leaf or leaves of the foliation, and has corners where it meets components of the binding. We also require some particular properties of our function, that its restriction to the boundary of the manifold is an S1 valued Morse function. And we're going to impose the same kind of conditions for supporting a context structure as previously. So this is small, not because it's not important, but because it's standard. It's saying, if we want to say that one of these things supports a context structure, then we're going to require the same conditions we did before, that the binding passes positively through the contact planes, and that the restriction of d alpha to the pages is an area form. Okay? But we have this new piece of structure. We don't just have the binding and the function, but we also have the foliation. And so now we want to also impose a condition on the foliation. So by definition, it's the level sets of the function restriction of the function to the boundary. Okay, and we want to say that it has to be close to the characteristic foliation. Okay, there's a precise way to do this, but let's say what this means first. Okay, so this is the characteristic foliation when I use this notation right here. And what you're supposed, if this isn't an object you've come across before, this is a pretty natural thing to consider. So if we have some surface, on the one hand, you have, at any given point, you have the tangent plane to the surface, but you also have a contact to plane at that point. And so if you look at the intersection of these two, it gives you some singular line field on the surface. And so there's a natural foliation that always arises on a convex surface from this foliation. And we want to say that the foliation that we get here, this open book foliation, in the terms of Ito and Kawamura, that this foliation is close. And for us, close is strongly topologically conjugate. So it says that there's a diffeomorphism of the surface in the mapping class group of the identity that takes the surface to the surface and the foliation to the foliation. Okay, sorry, and I said something completely wrong there. There's a homeomorphism of the surface, not a diffeomorphism of the surface. And that's really important because, in fact, it can't be smooth at the singular points. I'll pretend that was to make a point. It has to be a strongly topologically conjugate is telling you that these functions can't be, that these foliations can't be smoothly equivalent, but they are close in some sense. So at the level at which we can draw them, we can think of them as looking the same, but the behavior around the critical points is going to be subtly different. Okay. So, so my claim is that these things are rather nice to work with. So here's some theorems about them. And the upshot is that these give us the same kind of robust tool for studying contact manifolds with boundary that other forms of open books provide for the appropriate kinds of open books. So the first statement is that a foliated open book supports a unique isotopy class of contact structure. The second one is that every contact manifold with convex boundary admits a supporting foliated open book. We can make a stronger statement if we clarify what kind of foliations we allow. Then you can say every contact manifold with the right kind of foliation on its convex boundary will admit a supporting foliated open book. And we have a Giroux correspondence for contact manifolds with foliated boundaries. So if you have two compatible foliated open books, then there's that for the same contact manifold with foliated boundary, then there's a foliated open book stabilization, destabilization sequence that would relate the two of them. So these things should be used to study contact manifolds. And what I want, oops, I had one other thing I want to say there. And what I want to do is not prove any of these, but give you some indication of why this one is at least plausible. So this is going to be sort of proof by cartoon. So maybe that doesn't deserve the word proof, but I want to just tell you why you might think these things work. Because I think at first pass, this seems like an easy way to construct an object, but it's floppy. You can have all these different kinds of pages. They can change in lots and lots of ways. Why does this give us enough control to uniquely determine a contact structure?
Quick question, Joan.
Yes.
I think I know the answer, but this is a more general than the Giroux correspondence. Is it proved by using the original Giroux correspondence? It's proved
via the Giroux correspondence for partial open books. Okay. So one of the things that I won't talk about in this talk is that the partial open books and foliated open books are, if you throw away the boundary data, they're constructions for the same kind of object, a contact manifold with boundary, and you can move between them with a little bit of work. And so the proof for the Giroux correspondence takes a foliated open book, does something to it until you can get a associated partial open book, uses the HKM construction, and then comes back. And I will note that the kinds of stabilizations that you can use are more restricted. So there are stabilizations that would preserve the class of manifold from a partial open book point of view, where we're only interested in say the dividing curves on the surface, but that would change the foliation on the surface. So we do have a little bit more rigidity here. Thanks for the question. Okay, so here's the claim for why you should believe this statement down here, at least why you should think that this data, the binding, the page, and the foliation has something to do with the supported contact structure. And really, what we're interested in is what happens near the boundary, because that's the only place where this is different from the other versions. So this picture right here is meant to remind you of what we said when we first set up open books. We said what an open book decomposition does is it breaks your manifold into two pieces. So there's a part near the binding, which I said is standard, and then there's this parts away from the binding, which is a foliation. Okay, and now what we want to think about doing in both of these kind of parts is cutting by some surface. So this is drawn here in blue as F. And what we notice is the following. Okay, so the contact planes it gives you a nowhere integral plane field because it's a contact structure. But away from the binding, this plane field is as close to being a foliation as is possible. So I said that we'd come back to this condition that that D alpha restricted to each page is an area form. And what this means is that, well, it means what it says, but among other things, it tells you that the contact planes don't flip over relative to the plane of relative to the tangent planes of a given surface. So they can wobble around relative to a page, but they can't rotate around and around. And what you should think of this as doing is giving some sort of bounds in how badly they can wiggle. Okay, so here we have this picture at the top where we say we cut through the pages with some surface, and now we just use this surface in the bottom picture to truncate as we did in this original construction. So we're throwing everything outside. And because the contact planes can't flip over too much, then it tells you that if you looked at the characteristic foliation on this blue surface, this is our new boundary, and you compare that to the leaf coming from the page, they can't be too far apart. Okay, and this is the sort of the idea behind why you want the characteristic foliation and the open book foliation to be close together, and why having that might control something about what happens close enough to the boundary. So the sort of theory here is that if you know the characteristic foliation on a surface, this actually determines the contact structure in a neighborhood of the surface. We don't know the characteristic foliation when we only have the open book foliation, but it turns out we know that enough that when you combine this with the other open book conditions, you actually control what contact structure you have. Okay, so as I said, the goals were set up to guarantee success. It's always nice to, do something and then write your goals after the fact so you can check them off. But this is what I meant by having an easy construction of an open book for a contact manifold with boundary, is that we take the objects we already understand and just cut something out of them. Okay. And so now we want to move on to maybe some of the harder ones. Okay, so let's say a little something about gluing. So as described before, for us convex is just going to mean that you have this little buffer. And so here, this is what I meant by vertical, is vertical in my screen, the contact structure doesn't change as you do some little translation. And the idea here is that when we want to try to glue contact manifolds along convex boundary, in general, we don't have to keep track of all of the data. We only have to keep track of enough data if we're willing to do some perturbations to glue. So if you want to be able to glue as many things as possible, then you should try to impose as few constraints as possible. And so one of the ways this is done is by focusing only on the dividing set of a convex surface rather than the full data of the contact structure. So I should say most of the stuff I'm talking about, convex surfaces, can be traced back to Giroux one way or another. I think I didn't do a good job giving precise credits here. Okay. So I'm going to use the symbol gamma, as everyone does, for the dividing curve of a contact structure on a convex surface. And the simplest way to think about this is that your characteristic foliation is going to be a singular foliation, and each of the singularities comes with signs. So in the case of elliptic points, the signs come, the characteristic foliation is oriented also. This wasn't obvious from my initial picture, although I think I stuck an arrowhead on, but we can distinguish between sources and sinks, and we call sources positive and sinks negative. For hyperbolic points, if you just look at the orientations of the leaves, you can't tell what the sign would be, but in fact there is a well-defined sign. So if this is your tangent of your surface and it has a singular point, actually, if I'm going to draw a hyperbolic point, let me draw a hyperbolic point. Okay, so let's suppose that we're looking at a hyperbolic point in our surface right here, where the tangent to the surface at the saddle point, it actually agrees with the contact plane. That's how we would be getting a we'd be getting a hyperbolic singularity. The question you can ask is whether these are oriented in the same direction or in opposite directions. And if they're oriented in opposite directions, then we get a negative hyperbolic point. If they're oriented in the same direction, then we get a positive hyperbolic point. So you have your characteristic foliation. It has some collection of singularities. And if you take any multi-curve that separates all the positives on one side, all the negatives on the other, and is everywhere transverse to the remaining leaves, then we call that red multi-curve a dividing set. And one of the things that is great about dividing sets is that it's a very small amount of information to keep track of that tells us that we're still allowed to glue, okay? So if we have two contact manifolds with boundary and they have isotopic dividing curves on the boundary, then we can glue the two contact manifolds together. So this local invariance near the boundary says that these two things can glue together and get a well-defined contact manifold. Okay.
You mean if there's a what's missing from this is a diffeomorphism boundary of M2 to boundary of M1.
Sorry, when I said isotopic dividing curves, sorry, sorry. I didn't mean that one of them's a circle and the other one's a circle. What I meant is, suppose you have two manifolds that you might be able to glue. What we want to know is, and you have a contact manifold on one of them, and a contact structure on one, and contact structure on the other, and we want to know if we can put them together and to get to one contact manifold. So you're completely right. This was a lazy way to describe this. I'm assuming that we have a diffeomorphism from one to the other, and what I want to know is, when I look at that diffeomorphism and I compare the dividing set on one and the image of the dividing set on the other, what do these look like? And if they're isotopic, then I can actually glue them up so that the contact structure just extends. Thanks. That's obviously an important point to make.
Can I ask kind of a silly question for clarification?
Please.
Is it possible to define this without even having a binding?
Possible to define an open book?
Yeah, an open book with boundary where you just have the pi map and there's no binding.
So, okay, I mean, who knows what one could define, but here's why I suspect not. So, for a contact manifold, the nowhere integrable condition on the plane fields qualitatively means that they have to twist. Okay, and what you get out of the contact, what you get out of the binding is you have this point where they're transverse, and then as you move radially away, they immediately do some twisting. I say immediately, I mean in some neighborhood. They at the binding, they have this transverse property, and as you move away, they're going to rotate, okay? And the d alpha being an area form is what I described as saying that then they're sort of bound to match the page elsewhere, although there's still going to be some slight twisting, but they can't rotate over and over and over. So if you impose that second condition on pages, like you said, we have some pi map, we still break it into some surfaces, we still want the planes to not rotate too much with respect to the surfaces. If you got rid of the binding, you'd lose the place where they could rotate enough to make them a contact structure. So that's sort of a heuristic thing. The way I think of an open book is that it says globally as these plane fields move through the manifold, they have to twist. The binding kind of localizes the twisting and says you can think of the twisting as mostly happening right in a neighborhood of the binding, and you don't have to think about the twisting too much elsewhere. So if you kept don't twist too much elsewhere but got rid of the binding, I suspect you wouldn't be able to guarantee you'd get a contact structure.
Joan, I mean,
Yeah.
if you haven't active vibration, it still carries a contact structure, right?
Oh, I mean, as a manifold, sure, but I mean, if you have a vibration,
It says that not every contact structure can be achieved this way. You need to have a binding to say that every contact structure has blah blah blah. But you can build a contact structure without the binding on even a closed manifold if the manifold is a vibration and
not with the strict supported condition, because you need d alpha positive on the surface.
I Wouldn't that turn it into
Right.
into like a foliation or a confoliation if you?
Yeah, I think you're gonna have trouble. I mean, if everything's closed and if you have to have the
Yeah,
rate
no. You have to have a dividing set on the
on the boundary.
surface in order to be able to glue. Yeah. I mean, you cannot have a foliation without pluses and minuses, everything on a closed surface, right? I'm just talking about a surface with boundary, right?
Sure.
Anyway, whatever.
Can I ask a quick question?
Sure.
too?
I can't
That's
see who this
different.
is, but go for it.
So you're talking about how like the pages or how the contact structure can't twist too much away from the binding.
Yeah.
Does this mean, I don't know too much about the classification between over twisted and the other one, but does this mean that these contact structures can't be over twisted, or what does over twistedness look like in
No,
this?
so what it means though, I mean that's a great question. Open books let you talk about any contact structure. So not, you don't have to decide ahead of time if you're talking about over twisted or tight ones. What you do know is that if you have an over twisted structure supported by an open book, that the over twisted disc has to intersect the binding. So you can't, you're never going to be able to find an over twisted disc that's completely disjoint from the binding. Yeah, so there you go. Okay, and I got you in the chat. So I think I'm free. Other questions? Okay, so then let me just make a pitch for the utility of.
So just going back before the
Yeah.
question. So if you know that, I mean, in order to glue, you have to have a diffeomorphism of the boundary, and then you just need to know that under that isomorphism, dividing sets are isotopic, because the dividing set is only defined up to isotopy anyway, right?
Sure. Yeah, I guess that's a good point. I think of my I usually think of choosing a curve to be my dividing set, but Gordon's comment is completely right. Dividing sets are only defined to be things that satisfy these conditions over here, and so that already guarantees it. Yeah, thank you. Okay, so let me just say the downside of this kind of gluing. Okay, so suppose you have these two manifolds, like at the top here, where there's a diffeomorphism in the boundaries, takes a dividing set to dividing set up to isotopy. Then we know we can glue. Okay, and so now we have three manifolds we could think of. We have the original two, and we have the glued up manifold. And to each of these, there's an open book of some flavor. So I said in this sort of 2019 version, we have partial open books for the original ones, and we have a honest open book for the glued up one. But in complete generality, you can't assume that the partial open books for the two original ones would naturally give you an open book for the glued up one. So there are circumstances in which you can do this, but if you just sort of naively take the simplest things to glue that you can, you have to leave the world of open books as soon as you glue up. Then you could impose a new open book on the new one because you know every contact manifold has an open book, but the structure you started with doesn't naturally give you an open book structure on the glued up manifold. And this is one of the things we get out of foliated open books, is that if you glue two foliated open books, you're going to automatically get an open book for the glued up thing. So this should seem quite plausible from the construction, but let me try to sell it just a little bit. So if we have two contact manifolds with foliated boundary, and they have matching foliated boundaries, okay, so what do I mean by matching? I again mean that there's a diffeomorphism of the surface taking one to the other, and when you do this, you take the foliation on one leaf-wise to the foliation on the other, but with the signs of the singularities reversed. So elliptic points go to elliptic points, sources turning to sinks, hyperbolic points match with hyperbolic points, a reversing sign. Okay, so if you have matching foliated boundaries in this sense, then any two associated foliated open books glue page-wise to give you an open book, foliated or not, depending on if there's other components, for the glued up manifold. So your gluing can live completely within the world of open books, and you get that structure automatically on the result. So this is actually something that should seem plausible if we think about where these singularities come from. Okay, so here's the gluing picture for elliptic singularities on the first row, and the gluing picture for hyperbolic singularities on the second row. Okay, so how do we get an elliptic singularity? We have the binding coming, the oriented binding coming into the boundary of the manifold, and you see the pages give us these radial leaves. How do you get a negative elliptic singularity? You have the oriented binding exiting from into the interior of the manifold, and so you can just put these two things together, and you get that the binding passes through this thing, and this is now playing the role of that sort of initial separating surface that we looked at in our torus example. In the case of the hyperbolic singularities, it takes a moment's more thought, just because we have what's happening with the pages is a little bit harder to visualize. So here, what I want you to think of is that this vertical direction is the t direction. And so as t increases, you pass through a hyperbolic singularity exactly when your page is cut along some arc to separate it, and you pass through a negative hyperbolic singularity exactly when you're joining two pages along some one handle, that you're adding some one handle into the pages. Okay, and if you put these two things together, matching up the leaves of the foliation, then it's like a puzzle. You just take these two things and you click them together, and what we see is that the topology of the page then becomes constant as you pass from the brown page up to the blue page. Nothing ever changes. Okay, so
you take your right hand block and rotate it 90 degrees and then slide.
You have to rotate it to fit it. So if you try to jam it together, you'll end up with something that looks like genus in the middle. So I want to actually rotate it so they click together. Yeah, thanks. I think you had a student who made nice 3D printed things. I think I should put it in order for something like that. Okay. So so what this says is if these were your only boundary components of your manifold, then what you can see is as you travel, after you glue this together, as you're traveling in the t direction, then your topology of your page would never change. So the kind of change in the topology of the page that happens if you go through a positive hyperbolic point is exactly canceled by the kind of change in the topology as you would go through a negative hyperbolic point. Okay, so this brings us back to this sort of layout, and we've done some of these things. So we have a notion now of a contact manifold with foliated boundary. We can describe these by foliated open books. One of the things I haven't really talked about at all is the vertical arrows, but this is a little bit easier to say now. So if you have a foliated boundary, this is right over in the lower left corner. If you have a foliated boundary, we know that foliated boundary, if it's supporting a contact structure, is close to the characteristic foliation. And in fact, it follows from the definitions and a little bit of work that a dividing set or a dividing curve for this foliated boundary is always going to also be a dividing curve for the characteristic foliation. And so you can just forget about the foliation and recover a contact manifold with convex boundary. So there's more information being tracked when you keep track of the foliated boundary, but you haven't lost the information that you would have had if you only wanted to keep track of the dividing set. Okay, and along with this is an operation that takes us from foliated open books up to partial open books, and it really goes with forgetting this idea of the. Let me say it slightly differently. So we said that the topology of the page changes each time your foliation goes through a hyperbolic point. Okay? So in a foliated open book, the topology of the page can change many, many times. In a partial open book, for those of you who are familiar with them, the topology of the page changes twice. There's a big page and there's a small page. So at first approximation, you can go from a foliated open book to a partial open book by taking all of those changes in the topology of the page and trying to say, we're going to do all the hyperbolic points, positive hyperbolic points once, and all the negative hyperbolic points another times, and extract from this a partial open book. You can't always do this, but you can always stabilize a foliated open book to the stage at which you can do this. So there's a kind of ghost partial open book sitting inside a foliated open book, and vice versa. So what we haven't said anything about, and I think I have just about the right amount of time to sort of wave my hands at a few things, is where we get bordered sutured invariance from this. So let me give an unreasonably crash course in the HKM construction of contact invariance, and this is the one that we're going to adapt to give us contact invariant in the bordered sutured Floer homology from the foliated open book. Okay. So the starting input data for constructing a Heegaard Floer theory is a Heegaard diagram. And so our Heegaard diagram is a surface decorated with some red curves that are describing how how a handle body H alpha glues in, and some blue curves that are describing how a handle body H beta glues in. And in the original version of Oswald Szabo's contact invariant, they constructed a particular kind of Heegaard diagram and used this to find invariant, but the Honda-Kazes-Manich construction uses a Heegaard diagram that comes naturally from an open book. So this has turned out to be an extremely valuable and flexible way to work with things, and so I want to try to very briefly say how it works. So if you have a page of an open book, this is my schematic picture in the lower left. So my page here is meant to be a torus with a disk removed, and the idea is that we just, in an open book for a closed manifold, we just rotate this all the way around the binding, okay? Now, in this case, if you take a surface and you rotate it halfway around, that's just taking a product with an interval, so you'd get a handle body. If you take the surface and you go the other way, that's also giving you a handle body. And so the question is just, is there a nice way to give a Heegaard diagram that captures this particular decomposition into two handle bodies? There is. And so I just want to say this very quickly. Okay. So the first thing, and apologies for corners that are cut here. The first thing is that you choose an arc basis on your page. So this is just a collection of arcs that cut it into a disk. Okay, and these are going to be half of your attaching curves for your red curves. Then you take, each of these gets a buddy. So for each of these red curves, you take a blue curve, which intersects it once transversely. You can see I have these little intersections right here. And there's orientation conventions and directions for the perturbations. And that's really the data that we already had on the picture. This is sort of the stuff that seems nice and clear. We've got this surface with these curves on it, and we have to figure out how we actually turn this into a Heegaard diagram. And so things get a little messier at the next step. So for the red, we're thinking of the red handle body as the identity, where we just push the surface around, halfway around the curve. And so the red curves just get translated to the other, to the opposite page as themselves. The blue curves, remember that we don't have our open book is not a product, it's a fibration. So there's some monodromy map as you go all the way around the circle. And so when the blue curves come around, they glue up to that page on the left by some diffeomorphism denoted H. And so I've drawn something, I think the picture I actually drew here doesn't connect, but it's meant to be complicated enough that you can't tell that. So we have these nice red curves on both sides, we have nice blue curves on one side, and then we have no control over what happens to the blue curve on the other side, but we're guaranteed that what we have is a Heegaard splitting, and these alpha curves and the A curves and the B curves trace out compressing disks for these two handle bodies. So this is the diagram, okay? So this is the HKM construction of the contact invariant in the closed case, and I've highlighted in green the intersection points that give a generator in a chain complex that turns out to be the invariant. So this is absolutely a construction from an open book, but it's independent of all the choices, and it gives an invariant to the contact manifold. And what we want to do is try to replicate this in the case of a foliated open book. And Dave, how much time do I have? 4 minutes? Is that?
We started late. I mean, go till 4 o'clock. Go to the hour.
Okay. Okay, sounds good. I'll go to the hour then. Okay, so this is the difference between a foliated open book and a standard open book. This picture somehow says it all. So in a standard open book, you have all of these pages. So this is I'm going around in the S1 direction. You have all these pages and they're all exactly the same. It's the point of being a fibration. And in a foliated open book, our topology of our pages changes as we go around. And so you have these sort of bigger ones and smaller ones and so on. And the idea is that we exactly can keep track of how those pages change by looking at what happens to the foliation on the boundary. So as we've seen before, we had, okay. As we'd seen before, as you go through a positive hyperbolic point, the page gets cut along some arc. As you go through a negative hyperbolic point, the page has some one handle added to it, okay? And so what we do is we can see what's happening to the Euler characteristic of the page just by looking at the sign of what happens on the foliation. And so what we want to do is something like the following. This is going to be how we're going to construct our Heegaard diagram. We're going to take some page, and here you're supposed to see that I'm going to take 2 copies of a page, just as in the other construction, but I'm not going to take opposite pages. I'm going to take 2 pages that are actually very close together. So I'm going to label them as S0 and S epsilon here, and that just means that they're 2 parallel surfaces. They're topologically the same. There's no hyperbolic points in between them. Okay. And so one of my handle bodies is just going to be that very small product interval. I go from S0 to S epsilon, and this is a very small, simple product handle body. The other handle body, and so my Heegaard surface is S epsilon minus S0. They're topologically the same. They're just have different labels, so we can keep track of which one is slightly more positive. Okay. My other handle body is going to be everything else, and this is where we have to work a little bit harder. So in order to describe what everything else is, let's do the following. Okay. We're going to mess with our open book just a little bit. Okay. So if we start with a foliated open book, we can change the function pi to be actually an S1 valued Morse function. So before it was a regular function which restricted to a Morse function on the boundary. Now we're going to modify the function pi in the neighborhood of the boundary so that it's actually globally an S1 valued Morse function, but it has no interior critical points. The only critical points this Morse function are the critical points on the boundary, on the restriction to the boundary that we already had. Okay. Now, why would we want to do this? Because as soon as we have a Morse function, we have things like critical submanifolds. And so the difference between the picture on the left and the picture on the right is that now if I see this positive hyperbolic point on my surface, I can actually realize that this is a critical point of a Morse function. And for an appropriate choice of gradient-like vector field, which I'm going to completely sweep under the rug what appropriate means, I can look at the descending critical submanifold. For a negative hyperbolic point, I can look at the ascending submanifold. And what we notice is that if you take this submanifold here going down and you look and you cut the page at the bottom by its intersection, well, if you look at the complement of that cutting curve, the topology hasn't changed. That's just what Morse theory does for us, right? And similarly over here, if you look at the ascending manifold and you cut along the curve where it intersects the page, then the complement of that arc again has the same topology. Okay. So what this says is that if you look at how if you let these critical submanifolds flow through the manifold, cutting as they go, what the things that they don't touch, those parts of the pages are going to have constant, are going to remain homeomorphic. Okay, so here's our definition, okay? And it's definition with a star because I'm not telling you what kind of gradient-like flow we need to use, okay? So we say a Morse foliated open book is sorted if for the right kind of gradient-like flow, all the critical submanifolds can, embed disjointly in the complement of this sort of initial page. So this is on the next page. Let me just show you what this gives us. So this is our cartoon, okay? All of these green curves are things that start on the boundary, that's at a critical point, and we have this thing that's flowing, this is some sort of surface flowing through the manifold until it hits our special pages, our S epsilon or S0. And when our manifold is sorted, it says these things don't crash into each other. If we have a descending manifold, a descending critical submanifold, it can flow till it hits a surface. It won't hit the ascending manifolds. They just sort of pass around each other. And the observation that makes this work is that in the complement of these critical manifolds, we just have a product. We just have when they hit this S epsilon, this S0, we have some pieces that are left over, and those things just travel unimpeded all the way through the manifold as a product. Okay, so this is the Heegaard diagram associated to a sorted foliated open book. And I'm going to just cheat ahead for you because, okay. So we use this observation to construct the following thing. So on our 2 pages, we start with exactly these cutting curves that we just identified. These were the cutting curves from positive hyperbolic points when they flowed all the way to S epsilon. The gamma minuses here were the cutting curves for the negative hyperbolic points. We flowed them all the way to S0, so flowing them around in this direction, and then we applied the Goulding map H. Okay, so this is basically said that even though our topology of our surface was changing as we went around, once we've cut by these critical submanifolds, what's left is a product. Okay, and the rest of this column is just basically applying the HKM construction to that product. So we take a basis, we take perturbations, we push the basis arcs around in a simple way through the red handle body, we push them around by the monodromy in the complicated handle body. Okay, and what we end up with is a diagram that looks like this. It's a little bit ugly because there's a lot of different kinds of curves floating around, but it's a Heegaard diagram. The fact that topologically it describes the right manifold comes almost for free. And what I've completely hidden is why this is a nice one for bordered sutured Floer homology. So we have these sort of extra intervals that we decorate on the boundary, which are gamma. These become sutures in the bordered sutured Floer homology. The relevant point here is that we had these particular curves on the boundary, curves of the foliation, the separatrices at the hyperbolic points. Those are the things that are going to turn into some of our blue curves in this Heegaard diagram. And this is going to give us the bordered part of our diagram. So these curves that we started with that came from the foliation are going to give us our parameterization of our surface that allow us to glue. If you're not a bordered sutured Floer homology person, that probably didn't add much to your understanding. So let me just finish up with a few results. So these were grayed out because I wasn't sure about the order of things. But what do we end up with? So when you construct a diagram this way, which is really by analogy with the HKM construction, but in the context of a foliated open book, then you get distinguished generators just the way we did in other settings. And these give the classes of these generators are independent of all the choices, and so they give invariance of the foliated contact 3 manifold. So if you have 2 manifolds which can glue in the foliated open book sense, so they have these matching foliations, then the pairing theorem in bordered sutured Floer homology gives you a pairing between these 2 invariants, the CD and the CA invariant, and these will recover the original closed contact invariant. There's a little bit of work because you end up in a sutured invariant, then you make the change from sutured manifold to a multi-base point one. So there's a few steps here, which is why I use the word recover, but you can get back the original Heegaard Floer invariant. And then finally, if we want to, we can also recover the, if we glue an appropriate cap in the sense of Zarov, then we can recover the partial open book contact invariant due to HKM. So that's probably the right place to stop. So, thanks.
Thanks a lot. So are there questions for Joan?
So is this bordered sutured cap what we call protecting the boundary layer?
I don't think so. I think this is, so Akram might want to weigh on this also. She wrote part of the paper, but Ruman has a thing which says that if you have a bordered sutured manifold, there's a cap is something you can glue on, which basically kills the bordered part and turns it into a strictly sutured manifold in some natural way. And so the cap here is, and the cap involves choosing some set of the parameterizing curves in the original parameterization of the surface. And so for us, if we take the cap that's associated to the positive separatrices of the positive hyperbolic points, so this is really foliation specific data, then we end up with just a strictly sutured manifold, which is associated to
when we have we do part open books too, we sort of choose a decomposition of a product layer you stick in between, and I think this product layer we sort of have to choose basis for a boring away from a disk, and in order to put in a layer, and I think that's what this is, but I have to study what you did in order to.
Okay. Yeah. So I'm not sure then. It's possible. I'd be interested to chat. I was looking forward to talking with you a lot in Bonn, and that didn't work out so well. So
yeah, same here. Right. Maybe we should Zoom talk.
Let's try that sometime. That'd be great. I'd really enjoy that.
Yeah, that would be great. Yeah, that was my plan for those 2 months. You know.
Plans, right?
Right.
So I had a question. I mean, an interesting class of contact manifolds with boundary are like contact, let's say S3 minus a neighborhood of a Legendre knot or a transverse knot or something like that. Does this help you in any way understand, those things, not complements, or any idea?
So, okay, so we have ambitions, but I think the short answer at the moment is no. I think if you look at the complement of a transverse knot, if you just take a transverse knot, naturally what you're going to end up with is, well, there's some slope, I guess. It's not obvious how easy it is to get a neighborhood of a transverse knot to have something where you have the foliation with no circles. But I think Jeremy Van Morris's thesis had something along these lines where you looked exactly at neighborhoods of transverse knots where you had things, the foliation was only by circles. And so I think that's the place where I know that that's been done. We have some other work planned, which involves looking at like surface cross interval. Like surface cross interval is a surprisly interesting contact manifold.
Yeah, that was the other question I was going to ask. Yeah.
Okay, so we have a list of surface cross intervals that we want to study. One of the things that is that in this work that is sort of surprising to us is that sorry, this isn't going back very quickly, is that the choice of S0 page really seems to matter. Like if you just are handed a foliated open book or a manifold with foliated boundary, you actually care about what the zero leaf is. And we can argue that you get the same invariant, but the argument is not at all direct. Like we can't prove that directly. The proof is choose some invariant. Like we can only choose that it gives us the same thing when we map it to other invariants. We can't see what the dependence on the choice of zero leaf is directly in our invariant, and that seems really odd. So one of the things we'd like to do is just understand it. Can you have a time shifting leaf? Like if you have a manifold with foliated boundary which has a zero leaf, can you just add something on that just says now the zero leaf has traveled forward? And this is surprisingly hard. I mean, it seems like it should just work, and it continues to not just work.
So should I think of the zero leaf as the smallest?
No, the zero leaf. So there doesn't have to be a biggest or smallest leaf but ideally if you had to choose one thing, the zero leaf should be the biggest leaf, because you have all of these critical submanifolds can come down and land on it disjointly. So it's this big, it's somehow morally a big surface that can cut into small pieces. And the pieces, and when you cut along these arcs that come in, what you're left with is the P in your, like the zero leaf is S, and what's left after you cut along these arcs is P for the partial open book.
Oh,
Any
so
other questions? Someone was saying something. I cut them off. No? Okay, before we thank Joan again, I just want to say, Joan, you're available to hang out a little bit and talk more.
Yep, happy to.
So I was going to propose that I might go make a cup of tea or get a beer. I haven't decided which. And
it's a little early for beer for me. I might refill my tea though.
Yeah, but I'll just leave the room open, not close it, and people who want to stay and talk more casually, either about non-math or math stuff with Joan, please hang out. But let's thank Joan again. Great talk. Yeah. I'm gonna leave my video on, mute my audio, and go get my beverage. Be right back.
Okay. Thanks, everyone.
Thanks, Joe.
So, Akram, do you know the answer to Gordon's question? Is this protected?
No, it's true. I don't know.
Anyway, I have Akram here. She's closer, but since we're all communicating on Zoom, it doesn't really matter where we are, right?
It's weird, right? So,
weird.
Gordon, you said you went to Ina's talk right before this?
Yeah, at the end when it got interesting to come over here. I don't really you know, like the interesting stuff comes at the end. So, and I stayed till the end. So it, you know, she went pretty slowly, and then by the time I had to leave, it's just when it got interesting. So, and yeah.
And sorry, the rest of it, I think I've met.
And they went. I just realized they weren't recording.
Yeah. I've met some, but not all of you. Is that right?
I'm Trent.
Yeah, Trent. Okay, so I certainly know everybody's. Maybe I have met everybody. Okay. Yeah. So I was just trying to check. Peter, have we actually met in person? I know your name, but I'm not sure we've actually.
Yeah,
paths.
very briefly. I was in Bonn. I think
You were okay. I was okay.
You were there for like how long?
2 weeks. That wasn't quite what we planned. It was. Yeah. Were you there for the whole year then?
Settling the beginning. Yeah.
That was a very strange and intense time to be there. I mean, like the fact that it ended up being so short was very odd. Like I just felt like I was living in a news story. You know, every day there was all this stuff to check, and then we left right as things kind of shut down. But were you, right. Gordon? Were you still there?
You came when people were in quarantine. The ones that went to this conference in Italy, right?
Yeah, that's right. That's right.
Just crazy. Yeah.
And Trent, were you also in Bonn? Certainly all of UGA couldn't be in Bonn. Okay, maybe I got bearded mathematicians mistaken. Sorry about that.
Yeah, no, it's fine. Yeah, we all look the same with our beards. No, I think maybe Jason Joseph is who you're confusing me for. He was a grad student that was there. I don't know, maybe.
Who did? Okay, you thought Trent.
I was just trying to figure out who had actually seen the person.
All these
Peter didn't have a beard in Bonn, so he looks very different.
Yeah.
Okay. Oh, okay. That makes me feel much better. Okay, then yes. Then
well,
as long as
in March I didn't have a beard, but
that's what I mean. When she was there,
that's when I was shaved.